Oh, hello, hello. Um, I hope this is working. So, am I live? Is it going well? Let me just check. Hang on. Yeah, it looks like it's streaming as I expect. Yeah, as I said, it's a very different stream today. Um, as you'll notice, it is not a gaming one. It is something very, very different. Um, yes, so this is a math stream. Wow. How different. So yes, the aim for this is essentially to go over a maths paper. So this is the A level in England at Excel. We're kicking off with paper one. I'm not sure how much I get this done. Uh, but yeah, it is just a run through. See, I'll try to do my best to explain, go over the paper, do the questions, so forth, because obviously there are exams coming up very soon. So you know what, anyone watching helps anyone. It is what it is. But yeah, it should be on obviously on Twitch and stream at the moment, but it will be on my YouTube. I'll create a playlist for it. But yeah, as for gaming, probably tomorrow or whatever, whatever. But yeah, very, very, very different stream to usual. But yeah, I don't know, not much to say. But there is going to be some teething problems that I feel like. So yeah, today I bought this little graphing tablet thing. It's like this thing you write on with like a stylus pen. I haven't really used it, so we'll see how it goes. Like, it's probably not going to be the best, but you know, it is what it is. Um, but yeah, uh, Skelly, so I just can't believe how different this is to my other streams. But yeah, this is the aim to do some of these from time to time as well. A level GCSE, whatever, whatever. So yeah, this is the A level. So obviously, this is paper one. So this assesses pure. So this is things like differentiation, integration, vectors, trigonometry, algebra, functions, modular series, all of that sort of stuff. And so you get 2 hours to do usually about 14-ish questions. So yeah, so this is the 2018 paper. This was the first one ever released for this specification. So yeah, I guess I'll get into it. Obviously, the chat is there for any questions. I'll try my best to answer if I can. But yeah, or if it's obviously in the comment section, if after the stream you're watching a playback or anything, I'll try my best. Because obviously the whole point of this is, help people understand essentially. So yeah, I guess probably get started. I should probably say as well, with all these papers, you have a formula book, right? For A level, for the normal standalone maths. Um, these are the 3 pages you'll need, which we'll refer to throughout. But yeah, that's the preliminary stuff out of the way. So yeah, I guess let's get started again. It's probably not going to look the best, but it's my first time on this sort of thing. I'll try the best I can. Obviously, the aim of this as well. I'll try to do. So this is like a kind of unseen one. So obviously, I probably won't get everything right, naturally. This is the aim to show what you should be thinking, how you should be thinking, how you should write stuff, and how like you tackle paper rather than just giving the answers and being like, oh, you know what I mean? There you are, like. which some people do, which to their own. But yeah, I'll try my best to explain and do it. You know what I mean? So yeah, I guess I'd leave it there. I'll obviously also a calculator you'll need as well. Hopefully at this point, I'd be a bit concerned if you've got your exams in a few weeks and you know you're not aware you need to use the calculator for these papers. But yeah, I got a class whiz, not that fancy fucking what's it called, that graphical calculator stuff. But yeah, but any graph sketching is gonna be quite awful though. I don't know. We'll see how it goes. But yeah, let's jump into it, I guess. Okay, so the first question, given that feet was small, measured in radians, use small angle approximation. Find approximate value of the fraction. Okay, so this is quite a nice question. For question one. So I should immediately recognise its small angle approximations. Now, in the formula book, they get given you them here. Sine for cos and for tan, rightio. So it says we want 1 minus cos 4 theta over 2 sine 3 theta. So we're going to have to replace the cos 4 thetas and the sine 3 thetas using these formulas. Okay, so let's just get jumped into it then. So you would want. Oh, hang on. It might help if I write in pen rather than scrolling. That should be good now. Okay, so let's see, teething problems. Uh, okay, hopefully that should be good now. So yeah, let's do the fraction then. So 1 minus. Now we're going to replace the cos 4 theta with the small angle. So if we know cos theta is 1 minus theta squared over 2, we have cos 4 theta. So we want to replace the theta with 4 theta. So it will look something like 1 minus, what was it? 1 minus, instead of theta squared, you're going to want 4 theta squared. That'll be all over 2. And then over 2 theta. Likewise, sine 3 theta. So we know sine theta is theta, which then means sine 3 theta goes to just 3 theta, right? And now we just simplify. Uh, do, 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 do. So now notice the theta squareds will cancel out. So we get 8 over 6, which simplifies to 4 over 3. And that's how you do it. Do, 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 do. Okay, that's the first one. Let me check if I should have got that right. Yes, 4 over 3. Lovely, lovely. Uh, okay. Something to bear in mind with these questions as well, with these small angle ones. If they want you to give a value, you should be a numerical one. If you have it in terms of theta, you've probably gone wrong somewhere. So make sure you be conscious and check your answer to make sure it's sensible. But I hope that's how it should be. That should be fairly straightforward. Again, you should have practiced this, but and that should be a fairly standard question. Now on question two. Very, very lovely question again. So it's asking you to find a differential of a polynomial expression. Uh, Basic AS stuff. Hopefully, it shouldn't be too complicated. This might cause some issue, perhaps the root x, but that means you need to use your power law. So before I even start differentiating, You should make sure it's in differentiable form, so something you can easily differentiate. Okay, well, we can know that the differential of, so say if we have ax to the n, a standard polynomial term, the derivative of that is going to be the power law, so times by the power, so an x and minus 1. That's the form we want every term to be in. Well, x squared is already in that form, lovely, as is the 2x. Okay, but the root x is not. But we should know from third laws that, oh, it's messing. There we go. Make it clearer. We should know from third laws that root x goes to x to a half. Okay. So now we can differentiate each term. Cool. So dy dx. Now, so like we've done here, you times by the power, subtract by 1, so you get 2x, and then likewise is this, minus 2x goes to minus 2, and minus 24, so a half this, so minus 12, x to the minus a half. Now, we are fine to leave this in this form. We don't need to simplify anything. It just asks to find it. Sometimes it asks you to simplify it. Make sure you be careful. That would just be minus 12 over root x. That's what minus a half would do there. And then differentiate again. So d squared y dx squared means to differentiate the first derivative. So 2 means differentiate twice. Which we'll do. Again, it's all in index form, so I can just go ahead and differentiate. 2x goes to 2, minus 2 is a constant, goes to 0. And then minus 12x to minus a half, so times by minus a half. Careful with the negatives. Negative times negative goes to positive, so you'd have plus 12. Well, plus 6, because you're halving it now. And then that would go x minus 3 over 2, because you're minusing 1. And that's it. Then part B says, verify that C has a stationary point when x equals 4. Okay, well, you should know the state. A curve has a stationary point, so P is a stationary point if and only if, so if, for instance, if the derivative is 0 in simple terms. And that's what we're going to do here. So what we need to do then is we need to substitute x equals 4 in the first derivative. So we can say this as dy dx at x equals 4 equals, so then we substitute it in, 2 of, that's what this notation means, by the way. I'm substituting x equals 4 into the first derivative. So substitute in there, 2x, so 2 of 4, minus 2, minus 12, 4 to the minus a half. And if you put it into the calculator, let me just double check. You should get 0. Yes, you get 0. And also that obviously means your differentiation should have been right in the first part if that all matches up. Lovely. And then part C, so the nature of the stationary point. So when it says the nature of the point, it's telling us the behavior of the stationary point, which you get from the second derivative. So if d squared y, there's three possibilities, well, three different results you can get. If it's greater than 0 when you substitute the point in, that's telling you it is a minimum, because what that's telling you is the if that's greater than 0, then the rate of change of the gradient around that point. So say you got that point. That's telling you it's positive at that point. So the tangents, hang on, no, that's not right. Yes, greater than zero, so it has to be a minimum. I guess, yeah, let's study it. So that's definitely right. How do I want to explain it though? I've seen a lot of people would memorize it. So yeah, greater than zero is telling you that the rate of change of the rate of change is positive. Well, the rate of change is telling you the gradient is like what the gradient is around that the tangent is at that point. Which you know is zero because it's a stationary point. But I guess look around it. Du- 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 du. Hmm, not matching up with my intuition here. I'll come back to that. I don't want to spend too much time on it. But that is definitely true. Oh shit. But I'm not sure how to explain it though. uh, I'll come back to that because I'm not happy with that explanation. Likewise, if d squared y dx squared is less than zero, that's telling you it is a maximum point. Oh yeah, so yeah, so a minimum it would look like this, by the way. So it's like the x squared graph. Oh, shit. Uh, yeah, C is not going off with a great size. It would look like this essentially. It would be a minimum. So it's the minimum point in that area. Okay, so yeah, so this would be a maximum alternatively, which would look something like this. So it's the maximum value at that point. So it goes up or down or vice versa. And yeah, whereas this one's going down and going up. Uh, okay, and the last result is actually when it equals zero. Um, Now this is a bit more complicated. Equals zero. Now that it could be a point of inflection. Oh shit. But it doesn't have to be. Du- 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 du. What this is actually saying is, let me scroll down. Even around the, so it would look something like this, right? Like the x cubed or like the tan graph. What this is saying is, even around the point, the gradient around it is also going to zero as well. So the rate of change of the tangents around the point are also flat. See how the whole like neighborhood around the point is also flat. Whereas this is a sharp turn, so it's not a point of inflection. This one is kind of flat even around it. So even around points around it, the gradient would still be pretty much zero, which is where this comes from. Now it could be. So what you also need to test is around the points the gradient changes. So see how this is slowing down. So it's going from so the tangent's going from sort of like around the oh, never mind. Um, yes, so essentially, it's flat around it, so it's not like this with the sharp turns. Um, it's flat even around it, so it's a point of inflection. You also need to look at the derivative so that there's a change in sign as well. But bearing in mind, point of inflections also doesn't have to be a stationary point either. As long as it has this sort of effect where the gradient near it is near zero, but not exactly zero because you need to look at the tangent. So you substitute in dy dx around the point, so like x minus 0.001 and x plus 0.001, and you need to see. So this isn't about the question, but I'm explaining it. So you see, oh, x, hang on. So you need to substitute the derivative uh, a bit before the x and after the x, if x is the point you're interested in. Needs to be a sign change between both of them. Okay. Um, and yeah, that if both of these criteria are satisfied, if the second derivative is zero and there's a sign change at the derivative near the point, then it's a point of inflection. But you have to be really careful if the second derivative equals zero, it doesn't have to be a point of inflection. Whereas with these two, it it for sure is a minimum and a maximum. Um, okay, so that's just to explain the theory behind it. Again, I'll come up with an explanation for that at some point. Again, I'm not happy with that, but that's the results anyway. So yeah, so going back to it, so to determine the nature, that's what the nature means. It's asking to work out is it a minimum, a maximum, or a point of inflection. So let's substitute it in. So the second derivative is 2 plus 6x to the minus 3 over 2. Let's rewrite that here. 2, what was it? 2 plus 6x to the minus 3 over 2. Let's check that. Do, 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 do. Cool. So now you need to substitute at x equals 4. The derivative is it's going to be 2 plus 6. Oh, God. 6. Oh, hang on. No, I want to substitute it in. 6 up 4 to minus 3 over 2. Which then you can get your calculator right. It doesn't actually matter what the value is, unless it's zero, obviously. But you just need to see what sign it is, essentially. And apparently we get 2.65, which is positive. Now, what does that mean? If we go back, that means it's a minimum, right? The point has to be a minimum. God's sake, I'm not intending to delete it. It's just my pen's a bit fiddly, my stylus pen. Okay, so that's question 2 done, I believe. Let's move on. This one. So this looks like from first glance. So when you do enough of these as well, even just looking at the question from a glance, you should recognise the topic it's asking. So here, it looks very much like a radians question. So that's the good tip with these papers. Anything you do, really look at the topic that it is, and then think about all the ideas that you know about the topic, any formulas you know, or anything like that. So, oh, okay, let's leave it there. Okay, so showing a sector of a circle at radius r, the angle is theta and the area is 11. That's probably a key point there. It's giving us an actual fact there. And the perimeter, oh, just leave it there. Let's not underline anymore. The perimeter is 4 times the length of the arc. Okay, but we know some you should know from this two particular formulas with this topic that the area of a sector in radians is a half r squared theta, and you should know that the arc length, which is this bad boy here, AB, the curve, is r theta. And you do not get given that in the formula book, so you do need to remember that. So yeah, so essentially it's just substituting these, dealing with these two formulas here, and I reckon we're going to get simultaneous equations. But anyway, let's work with the first fact. So it's telling us that the area is 11. This has to be half r squared theta. Now we can tidy this up a little bit because we can get rid of this half by times it by 2, which means 22 then is r squared theta. Okay, that's the first one. Now it's also telling us that the perimeter is 4 times the length. Now we know what the length is, so the length or arc is which we can call L for the length, and that's just going to be r theta. Okay, but we also know something about L because it's telling us the perimeter is 4 times the length. So perimeter of this. So of the shape. So you add in all the outside bits. So that's just going to be the P is going to be R plus another R, and then this bit here, which we call L, right? So this is going to be L, which is 2R plus L. So then it's telling us 2R plus L is 4 lots of L. So 2R plus L is 4L, which means if we rearrange this, 3L is 2R, which then means L is 2/3 R. We also know this, so we can substitute it in. So we know that R theta is 2/3 R. So R theta minus 2/3 R equals 0. Which is actually sort of quadratic at this point. So we're solving, let's factorise for r. So r theta minus 2/3 equals 0. Now this is telling us either r is 0 or theta is 2/3. Oh, hang on. Oh, what am I doing here? I'm going to delete it. Hang on. There we are. There we are. Or theta is 2/3. Yes. Now r is 0 isn't really a valid solution because obviously then we wouldn't have a sector. There'd be nothing there. So this has to be the solution, which means theta is 2/3. So, and then we go back to the first formula. So we know that r squared theta is 22. Which means r 2/3 r squared, substituting theta in, is 22. And then that means r squared times by 3/2, 22, which simplifies to 33, I believe, right? 22 divided by 2 is 11 times by 3. Therefore, r is going to be root 33. Now, remind you not plus or minus in because you can't have minus because radius is a positive quantity. It's a measurement. It's a length. So this is the exact form of the radius, and that should be the question done. Okay. Now on question 4. So saying the curve of equation y is 2 ln 8 minus x makes the line y equals x at the single point x equals alpha. Show that alpha is strictly between 3 and 4. Okay, so this should be another standard question. So it's saying that the intersection point is alpha, I believe. Yes. And so we need to show this. So, if x, so y equals this. So at the intersection point at alpha, x equals alpha, y is equal to x, which means y has to be alpha as well. But also y is this. So it's saying alpha is 2 ln 8 minus x. Okay. So let's just write the equation down. Y is 2 ln 8 minus x. So at alpha equals 2 ln 8 minus alpha. Okay. Okay. So when you deal with these sign change questions, you want to with 2 points. You want to see that if you're given two in a range of values for a for a root, you want to verify it is in that interval. So we're saying 3 is less than alpha, less than 4. If the function you're dealing with has a sign change. So the best way to do this is to call let f of x, or should I say f of alpha, equal alpha minus. You don't have to do this. I think you should be able to pick up the marks for that. But just to be clear, because what you're going to do then is you want to see it's above 0 and less than 0. So let's see what f of 3 gives us. And that's really messy. So it's 3 minus 2 ln 8 minus 3. God's sake. Which you can put in your calculator. What does that give us? Minus 0.21 something. Likewise, f of 4 is going to be 4 minus ln 2 ln 8 minus 4, which gets you, put that into the calculator, gets you 1.22 something. Okay, so we notice there's a sign change. The function has a sign change uh, in 3 less than alpha less than 4. Um, and this is the crucial bit, and it is continuous. For God's sake. There we are. Continuous messy writing. Although this whole writing's a mess anyway. I do apologize. I'll get better with it as I write more. This is, I guess, a practice more than anything. Anyway, it's continuous in this interval, right? And you can see this on the graph. So, if you look up, between 3 and 4, the functions are continuous, right? There's no jumps or gaps or anything like that. Which so 3 would be, well, zero's there, so 3 probably be like there. And the intersection's there. So it's continuous everywhere here, but particularly between 3 and 4. Now that is an important distinction to make, because if you're trying to show a a function has a root, I guess as an example, let's sketch this particular function. If say we did this, No, not that. Hang on. No, oh God. Say a graph looked like that. But then it missed the content. We jumped, right? We jumped here. But if you took the sign here and the sign here, one's positive and one's negative. So because of this test, you'd say there's a sign change, so there has to be a root. But there isn't because it doesn't cross the axis because it's discontinuous. So both conditions are needed here. So you just need to be really careful. And you need to make sure with these questions, when you talk about sign change, where the roots are, you also must write down that the function or whatever you're dealing with is continuous. Okay, because of these two are satisfied, therefore the root alpha lies in the interval, right? And that should for 2 marks. Hang on a second, then I just need to put the light on. Uh, Okay, let's move on to part B. So, we got a figure here. Shows the graph 2 learn 8 minus x and y equals x. A student uses the iterative formula xn plus 1, 2 learn 8 minus xn as a attempt to find alpha. And you should know this is making use of the cobweb diagram. Um, so you start with an initial guess for alpha in this interval. So say if like alpha's here, then you want to go up here, here, and it'll go. Hang on, I haven't done cobweb diagrams in ages, but that's the idea. Essentially, you're picking alpha. Oh, it hits the curve, doesn't it? Not the line. So the curve goes here. So the line goes there, and then they go back to the curve, the line, the curve, the line, the curve, the line. So yeah, cobweb diagram says you guess a root in the interval. Then it hits the curve y value. Um, then you need to make sure it goes to the line. Then you drop down, and that would be your second guess, x2. Then which hit the go to the curve again, and it forms this little box where it converges to the intersection point. And that's what these iterations are doing. That's the cobweb diagram. Again, that's not really the most clearest, I know it, but I get it. But if I come across it in the future, I'll try and explain it better. But that's essentially what's going on here graphically. That's what this algorithm is doing to find alpha. It's converging with each guess for x. It's converging to the intersection point alpha. Okay, so we should write the iterative formula, and we're given the first guess for. So let's write it down. So xn plus 1 equals 2 learn 8 minus xn, I believe. Let's just double check that. 8 minus xn. Great. Okay, so we said x1 is 4. And this should be straight from GCSE as well, by the way. So determine whether or not this iterative formula can be used to find an approximation for alpha arco. So it's not asking you to do the iteration. It's asking you if it can be used, which is an interesting question. Again, I guess you could think about it graphically. So to guide our answers, so again, do the cobweb sort of situation. So it should hit the curve first. Let me get rid of these then. There we go. Okay, so hit the curve here. Now, I believe it should follow. I don't think it goes up. Oh no, it can do because it's a staircase diagram, I think. So then it hits the curve there, Yeah, it should converge, I think. So that's like a spiral more than a cobweb. Or staircase diagram. I don't know, whatever you call it. So my instinct is to say yes. But you can also guess. Let's just test it as well. Before we give an answer with these type of questions, also always good to kind of verify it. So let's just use it. So x1 is 4, x2 would be what? Let's just shoot it in. 2 learn 8 minus 4, you get 2.7. Oh, x3 would be, and that would be 3.303. And you can start perhaps to see it's converging, right? X4 would then be 3.09 something. X5 would be 3.18. And you can start to see it converges, right? So the answer agrees with our graphical representation of the staircase diagram. It does converge, right? It keeps hitting. So the answer is yes. So I guess the reason for it, how do we write it down? Um, hmm, just to find your answer. I wonder if the graph would be good enough using a staircase diagram to represent it. Hmm. I would say yes. Yeah, justify your answer. So I guess you can refer to this. Yes, because uh, x1 is 4 uh, produces a convergent. Uh, oh, yeah, it's a staircase, right? It's a staircase diagram, which you can show graphically, right? Shown on graph to illustrate that it does converge. And these converge too, right? To verify it, and it the iteration, the numerical iteration converges too. I think that's what I would put. I don't know. I don't know what other reasoning I'd put. Uh, I don't know. I don't know what justification they're asking for there. That's what I would put. I think that'd be good enough, right? You draw the staircase, and you do the numerical approximations. That's the kind of thing. I don't know. I would look for anyway. I don't know. Let's leave it there. Oh, we've got a nice differentiation question. Given that y is this, show that dy by d theta is a1 plus sine 2 theta. So what you should notice is we have a fraction of theta on both sides, so it screams the quotient rule, right? Now the quotient rule is actually given in the formula sheet. So if you ever stuck, you don't remember it. It's down here, right? It might not be in the form you used to, but you work with it. So it's telling us f of x over g of x, the derivative of the quotient is f dash of x. So that's can I copy it? I'm going to try and flex my skills here. I could have done it before. I did it before. Remember, I did it accidentally. But I could like highlight the text box, so I assume I should be able to paste it, right? Uh, oh, here we are. And that's just drawing something. I don't want to draw it. No, not that. Hang on. Hang on a second. The idea behind what I'm trying to do here is I want to paste. Okay, it's not getting anywhere. I'm going to stop being lazy. I'm going to Okay, I'm going to just write it down. So what the quotient states is let's put it here. So it's saying that if we have f of x over g of x, the derivative is, or y dash is going to be, I believe it should be f dash of x g of x minus, is that right? F dash of x g of x minus f of x g, yeah, I remember that. Minus f of x g dash of x all over g of x squared. So all it comes to now is we can substitute stuff into this formula. So f of x is the top of the numerator and the g of x will be the denominator, right? So f of x is, let's just label it, 3 sine theta, and g of x is going to be 2 sine theta plus 2 cos theta. Lovely. So we need the derivatives of both of them to substitute it in, right? So f dash of x, you should know the derivatives of cos and sine. So sine goes to cos, so 3 cos theta, and g dash of x. Hang on. It's a bit messy. It's going to be, well, 2 cos theta again. Plus, now cos theta goes to minus sine theta. Notice the sine, so it's going to be minus 2 sine theta. I guess you can remember it like cos, like this. You have to pay attention to the sine. So it's sine here. So you get sine, but you also have to remember the sine. So I guess that's one way to remember it. And yeah, so now we just substitute it in. So the derivative is going to be purely by substituting it in first. But we'll forget simplifying for a moment. So f dash, so it's going to be 3 cos theta of g of x. So it's going to be 2 sine theta plus 2 cos theta minus, oh god, there's no room, minus, I'll put it here, minus f of x, which is going to be 3 sine x, sine theta, sorry. 3 sine theta of g dash, oh, what was that? 2 cos theta minus 2 sine theta all over g of x squared, um, which will be 2 sine theta plus 2 cos theta squared. Now we have to think about the simplifying it. So saying the form has to look like this. So a over 1 plus sine 2 theta. Notice here it's double angle, 2 theta. So that is going to be our aim here. That's going to be what guides us, is trying to convert the numerator, the denominator, sorry, into sine 2 theta. But I think the best strategy here is to expand stuff first and then simplify if we can. So the derivative then, let's continue. So let's expand some stuff out. 3 or 6, sorry, because it's 2. 6 sine theta cos theta. And notice there's a very familiar looking double angle here. Plus 6 cos squared theta minus 6 sine theta cos theta. So they cancel out. That is a good sign, I guess. 6 sine theta plus 6 sine squared theta. Oh, squeeze it in there. Over and expand this, so it's going to be 4 sine squared theta plus 4 cos squared theta. Oh. And now this 2 sine theta times 2 cos theta before sine theta times 2 because you get it twice if you expand it. So it's going to be plus 8 sine theta cos theta. Cool. Now it looks a complete mess. Actually, we can simplify it again, actually, because these will go away, these sine theta cos theta. So you'd have 6 cos squared theta plus 6 sine squared theta over 4 sine squared theta plus 4 cos squared theta plus 8 sine theta cos theta. Do, 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 do. Okay, cool. Now, some identities will help. With these questions, you should be thinking of trig identities in the back of your mind. And this is probably the most common one. So, no, this looks very simplifiable, if that's a word. So, we should know that sine squared theta plus oh, cos squared theta. Oh, there it is, theta. That's always 1. And no, it's sine squared, not sine 2 theta there. And also, it told us the identity. It told us we need sine 2 theta, right? So it's going to be useful to think of the double angle for sine as well, I reckon, which would be 2 sine theta cos theta. Now these you should know. You can derive them. But I don't recommend it. The sine 2 theta comes from the addition formula. Let's just get it up. From here, right? So you get given the addition formula in the book, sine A plus B. Instead of A plus B, you'd want, well, A plus A or sine theta plus theta to get 2 theta. And you can simplify it that way. And the Pythagorean identity is a very, very rough sketch. It comes from a unit circle. So, unit circle radius 1. If you pick any point P on the curve, oh, God damn it, if I can get rid of it, for bloody P there, any point there, if the radius is 1 and it makes a right angle theta there, radius 1. Well, if you just use trigonometry, the point is going to be coordinate x, so that's going to be cos theta, sine theta. Okay, and we know the radius is 1 because it's a unit circle. We defined it to be. But also, if you do the Pythagoras, the x squared plus y squared, cos squared plus sine squared theta, that gets you the radius as well. So the radius must be 1, but we also know the radius by Pythagoras is cos squared and sine squared. So that gets you this identity here. And that works for any point on the circle, any p whatsoever. So it will always be true for any theta. So that's where that comes from. Sine 2 theta comes from the addition. But you should really know this by heart. You really should. Don't try and derive it. And it should be ingrained in your mind by now. But yeah, that's the identity we're going to use. And we can simplify this. So dy by d theta is going to be, well, we can factor 6 out, can't we? So that's going to be 6. Now, cos squared plus sine squared goes to 1. over. Now we got it again, so 4 lots of the same. 5 sine squared plus squared, that's going to be 4 of 1. And we've got 8 sine squared sine theta cos theta. Now 2 sine theta is sine 2 theta. So if we times by 4 each side, we'll get 8 lots of this, will be 4 sine 2 theta. Okay. Which goes to 6 over 4 plus 4 sine 2 theta. Now look at the question back again. It looks very, very, very similar to the form a over 1 plus sine 2 theta. And it tells us a is rational, so a is going to be a fraction, not a whole number necessarily. So the key again, use the question to guide us. 1 plus sine 2 theta. So instead of 4 here, we want 1. What can we do here? Well, you can factor the 4 out. First of all, 1 plus sine 2 theta, which is the identical denominator. And we can just bring it up here, right? So if we're doing 6 divided by 4 here, we can just write it up here. So that's going to be 6 over 4 over 1 plus sine 2 theta. So we just bring it up there, which simplifies 3 over 2, right? So that's telling you the constant here is 3 over 2, which is rational. So that's the derivative of that. It's very nice. Really, a nice quotient rule. You use the formula given, substitute it in, then do some. I don't think it's the trickiest trig proof, trig manipulation. I'd say fairly nice. I think the formulas stand out. No, I think it stands out what you need to use here. Pretty nice 5 marks, I'd say. And now we're on this one. Okay. So now it's saying the circle C, so it's a circle question. So think about that. We might just substitute equations in, use discriminant perhaps. So it's saying the circle C, drawn here, centre A, 5, 7, 5. We know the centre. We know the line here with the given equation is a tangent to P. So we can work a lot of stuff out from this, right? So what's it saying? Show that the equation of PA is this. So a line here. So there's some key bits of information we need here. Well, for any line, so it's asking us the equation of a line. All lines must have the form y equals mx plus c. All of it, where c is the y-intercept and m is the gradient. Okay. So, what information do we know? Do we know the y-intercept? No. Do we know m? Not on the surface, not obviously, but you should know the circle law that the line, a tangent at a point, and the radius towards the point are perpendicular to each other. So if we can work out vice versa, the equation, the gradient of the line, we know the gradient of the radius. But we do know the gradient of the line because we're given it's 2x plus 1. So the gradient of L, oh, of L is what, 2? Gradient of the tangent, which is PA, that's going to be minus a half, right? As perpendicular. It's best to write it as justification, but you don't really have to, I don't think. But that's it. So we know that m is minus a half. So let's complete our line. Now we just need to know the c. So what can we do? We're given a point A. Now A lies on the line because it's PA. So we know that A, which is 7, 5, oh, lies on PA, right? So substituting it in. So therefore 5 would be minus a half of 7 plus C. Which means C would be 5 plus 7 over 2. You should put the calculator. Gets you 17 over 2. Okay, if you solve that little equation there. And then we've got the complete equation, right? So bring it all together. Y is minus a half x plus 17 over 2. Now, you have to check. It wants you in a specific form, right? There, so you need to show that 2y plus x is 17. So the best way at the start, so bring the y and x on the same side to make it look like reminiscent of it. And now we need to times by 2 because there's no fractions here. So that means 2y plus x is 17. Now that I believe is the equation we're given. Nice, and we know we've done it right. Okay, lovely, lovely. So now it's looking for the equation of C. So let's go to part B. Again, you should remember by now that the equation of any circle has the form x minus a squared plus y minus b squared. It's r squared. So AB center. Pay attention to the signs here. The signs flip. Okay. It's center. R is radius. So remember r squared here, so you have to square root it to get the radius. So those are the two informations we need. Now actually, we're already given the center because we're told it's A. So we can again fit in this equation, right? So equation is going to be x minus, and we're given A, right? So A is 7, 5. So x minus 7 squared plus 1 minus 5 squared is r squared. Now we need to work out r. So, okay. So we know 1 point. We know the radius is the distance between A to P, right? So I think we need to work out what P is. And then we can use the Pythagoras to find the distance, right? Between A and P, which gives us our radius. Okay, wow, how do we find P then? Well, is it P is the intersection between AP and L. But we know what the two equations are. We know L, which is given, and we worked out what PA is as well. So it's just simple simultaneous equations, essentially. So we need to solve. What is it? 2y plus x is 17, and y equals. Let's go back here again. 2x plus 1, right? Always use most of the time they've asked you to do previous part of the question for a reason. You probably need to use the equation with the line here, right? They don't usually don't ask you to work out stuff for no reason. So pay attention. So yeah, so we solved this. So at A level, you really should be using substitution, not elimination or making multiples of stuff. Ideally, to solve simultaneous equations like this. Not always, but most of the time. But yeah, we've already given y equals, so we can simply substitute it here. So 2 of this. So 2x plus 2x plus 1 plus x is 17. So then expand the bracket. 4x plus 2 plus x, 17. Then we know that 5x is 15, which means x has to be 3, right? But then to find p, that's the x coordinate. So p is 3y. So y, if I substitute it back into any of them, so y is 2 or 3 plus 1. 6 plus 1 is 7. Therefore, P is 3, 7. So, then the radius is going to be the distance between, is going to be the distance, PA, right, the 2 points. Well, that's going to be, if you use Pythagoras, the difference in the x coordinates minus the difference in the y coordinates squared. So we know that P is 3, 7. And we know that A is, what was it? 7, 5. Okay. So Pythagoras dictates, says, well, difference of the x coordinates. So let's do PA, so 3 minus 7 squared, plus 7 minus 5 squared, so then difference in the y coordinates. Equals, let's simplify it. You can just pull it into calculator. That'd be minus 4, so minus 4 squared would be 16. 16 plus 2 squared, which is 4, which should go to root 20. That's your radius, R, right? Therefore, the equation of the circle go all the way back. Now we know both R and the centre. So it's x minus 7 and y minus 5. Now it's R squared. So the square of root 20 is just 20. And that's your equation of the circle. Lovely, lovely. Just as I guess anyone is confused about this as well. So between any 2 points, say PA again. So where's P? 3, 7. So it looks something like this. P. And then A's here. So the distance, wait, we can always between 2 points form a right angle triangle. So the distance is obviously by Pythagoras. Right angle there. It's just going to be the difference in the x coordinates, which in this case was 4. The difference of the y coordinate is going to be, well, what we would add 2. And then you square it. So then Pythagoras dictates you square both how you find the hypotenuse, which is the basic GCSE. You square the x coordinate and you square the y coordinate, add them, then root them. That's how you get your distance. So that would be root 20. Cool. Which we found here. That's the distance, the straight line distance between P and A, which is the radius here. So that's where all that comes from. If we're a bit unsure why we just immediately do this, that's where that comes from, the Pythagoras of the 2 points. Okay, so that's part B. Now part C, which I assume is a bit trickier. Okay, so the line with equation y is 2x plus k, where k is not -1. Notice, so it's different to L, because the key difference is k's, the y-intercept is different. It's also tangent to C. So, this is a very graphical type of question. Actually, no, I don't think so. Actually, because if it's a tangent to C, so say if a line is tangent to a circle, that must mean there is only, or no, yeah, there's only or exactly one point of intersection, which means if you equate the two together, the equation of the circle and the equation of the line, you will only always only get one solution if it is a tangent. Okay, and that's what we can do here. So, and this is why they asked for part B to find the equation of the circle. So now we can substitute it in. So we know y 2x, what was it, plus k is tangent. See? So, sub equations as follows, right? So, obviously, it was always substitute the line into it. So, x minus 7 squared plus y. Now, y would be 2x plus k minus 5 squared, which is 20. Just to check, that is the right equation, right? 2x plus k. It is nice. Du- 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 du. So yeah, so now it's just an algebra grind essentially. So just expand and simplify into a quadratic. So that would be x squared minus 14x. Oh, oh god damn it. Four yeah, 14x. Oh, don't want to cancel that out. Minus 14x plus 49. Plus, now this you do need to be tricky, a bit more careful of because there's 3 terms in the brackets. So I think with this, it's best to play it safe. So uh, du- 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 I'm going to do an off note here. So I'm going to say just to do some extra work in here. 2x minus 5k, 2x plus k minus 5. Sorry. The expansion of that is going to be 4x squared. There's times for 2x by in here, plus 2xk minus 10x, right? Now let's add the k's, plus 2kx, plus k squared, minus 5k. Then minus 5 times everything, minus 10x, minus 5k, plus 25. And then we can simplify it, right? So 4x squared, there's only one x squared term. There's two xk terms here. So 2xk, 2xk, that's 4xk, minus 10x, and there's another 10x there. That'd be minus 20x. Oh. Then there's a k, two k terms, minus 10k, plus a k squared, there's only one k squared term, and 25, there's only one constant. So that's the expansion of that. So let's add it to this. So 4x squared plus 4kx or xk, doesn't really matter. Uh, plus 4kx minus 20x minus 10k plus k squared. Oh, plus 25 oh, equals 20, right? And actually, we can simplify it, can't we? So we know there's x squared and another 4. X squared, so that's 5x squared. There's a minus 14x minus a 20x. So that's going to be minus 34x. We know there's a 49 constant and a 25 constant. So that's going to be what? 49, 25, 74, right? Cool. And then there's a 4kx term. Okay, that stays the same. There's only one. Minus 10k plus, was it plus or minus? Plus k squared, right? And that's going to be equal to 20. Okay. Okay. Hopefully you see that now, so I won't need any of this anymore, right? That's just the expansion. Let's get rid of all of this now to make more room. Uh, oh my God. What are all these signs? Random drawings. There we go. That should be all gone. So now it looks very, 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 very reminiscent of a quadratic. So let's make sure we clearly show it is a quadratic, right? So it's going to be 5x squared. That's the x squared term. Now, plus, what x's do we have? Let's group them together. Minus 34x plus a 4kx, so plus 4k. Add the coefficients. And we also have constant, right? We have then we have a constant term, plus k squared, minus 10k. Remember, k is a constant here, x is the variable, so this will be a constant. Then we have plus 74, but it's also 20. We can move the 20 over, subtract 20 to get 54 equals 0. So now it's identical to quadratic. Okay, now, because only one intersection means the discriminant, which is b squared minus 4ac, has to be equal to 0. So now what this means is we have another quadratic to solve, another bit to solve. So b squared, so that's this term here, right? Oh, I should put an x there. So that's going to be minus 34 plus 4k squared minus 4 of 5. And this bit here, so k squared. Oh, hang on. K squared. K squared minus 10k plus 54. That will, God damn it, has to equal 0. Okay. So now again, it's just another algebra. This is just a huge algebra grind. So uh, we expand this, and if you do expand it, you should hopefully get 16k squared plus minus 272k plus 1156. And then minus 4 times 5, so that's going to be minus 20, lots of F in here. So it's going to be minus 20 of k squared. Minus 20 times minus 10, so that's going to be plus 200. Okay. Minus 20 times 54, which is 54 times minus 20. That would be minus 180. 1080, sorry, equals 0. And yes, so now we just simplify some stuff. So 16k squared minus 20, that's going to be minus 4k squared. Minus 272k. Anyone does chemistry, it looks like Kelvin, what was it, the standard room temperature? If anyone does that. Minus 272k plus 200k, that's going to be minus 72k. Plus 1156 minus 1080. Which will be plus 76, right? Which looks like a more legit quadratic, right? At this point, the numbers aren't as big anymore. At this point, you just plug it to the calculator, I believe. I don't think at A level you need to use like show it, factorize it. If you can just jump into solving a quadratic, you can do. Yeah, you'd basically use a quadratic formula, but we can just use the calculator because the class whiz obviously has a polynomial solver. If we can just get that somewhere. Okay, so minus 4 for A, minus 72 for B, and 76 for C. And hopefully what you should get is k equals 1, which, and you'll see why that's a good thing in a moment. K equals 1, the solution, or k equals minus 19. Now, there are two solutions possible for k. However, look what they told us, if you pay attention to the detail. Oh God, scrolling pages. K cannot be 1. And that is because we already know what this is the tangent here. We want to find the other tangent. So we reject k equals 1, and that will be the and minus 19 will be our solution, right? If we can just scroll down. K cannot be 1, so k is minus 19. And that's it. Coolio. Okay, now we're given on this question. An interesting integral question, actually. Given that k and z plus, show that that integral is independent of k. Now, you might not know what this perhaps means. This might look like waffle, but if it shows that this integral, we can work out the integral. So, and look at the marks as well. So they'll probably expect us to work out the integral. So I think that's a very good point to start to do, right? Do the integral first and foremost. Pay attention to the waffle after. Okay, so let's work out this integral. So 3k of k 2 over 3x minus k dx. A lot of constants. So I think the best thing to do, obviously there's a factor of 2 here. Take any multiples out, that'll make it life a lot easier. 2 lots of the integral of 3k and k of 1 lots of 3x minus k dx. Now, recognise this. This looks like it looks like it integrates to log, right? So 1 over x oh, dx goes to learn mod x. And actually, you can scale it accordingly. So the integral of this, so if this is 1 over 3x, and actually you can do it two ways. You can even show it like this. So if you wanted to, you could take a factor of a third out, right? Just to really illustrate the point. 1 over x minus k over 3, right? Now, adding or minusing a constant does nothing to this. It's the same thing. Because what the idea is with this log rule, I guess more generally, right? More generally, if we have f dash of x over f of x dx, well, that is the learn of mod f of x, right? And this is a specific case. So differentiating x here gets to 1, so it applies to this, okay? What we're doing here is then, if we differentiate this bit at the bottom, we get 1, and that's it, because this is a constant, so it goes away, okay? So that's irrelevant. So this differentiates to 1, which is exactly this, so we don't need to do any more scaling. If we differentiate it here, you'd get 3. 3x minus k differentiates 3. Well, 3 is 3 lots of this, so we need to scale it by a third, which is effectively what we've done here. But either way, whatever helps, just remember this is what this question's asking, referring to. This log integral here, that's what you need here. And that should be a very key integral proper rule, if you will, when doing integration. So yeah, so now we can just substitute the limits in. So that's the integral of what was it? So learn of x minus k of 3. Also note you need modulus brackets, okay? Because sometimes you get a negative, but it's fine. because there's a modulus, it will flip it to be positive. So 3k and k. And yeah, that's all we have to do. So there we go. 2/3 of learn. Okay, 3k minus k over 3 minus, so substitute the upper bound and then minus the lower bound. The learn of k minus k over 3. Yeah. And actually, so I think we could simplify it, right? So, good thing if we don't know what to do at this point, it's better to simplify, see what we can do. Like with the tangent derivative, when we did the quotient rule. If you're unsure of what to do next, just try and simplify as much as you can, and then you might stumble onto the answer. So first of all, we can simplify inside. Just get it all in terms of one fraction. Um, so 3k minus k over 3 should get you 9k over 3 minus k over 3 should get you 8k over 3, I believe. Minus learn, and that's positive. So yeah. Okay, learn of k minus k over 3 should get you 3k over 3 minus k, 2k over 3. Okay. Okay. And that's it. And actually, we can simplify further because you should recognize the log rule here. If you minus two, two different logs of the same base, so e or whatever, you can actually bring them as a fraction together, and you should recognize that. Therefore, integral equal is 2/3, and we can bring them together, right? So we can say learn 8k over 3. Now, if you're dividing two fractions like this already, again, break it down. Be simple. If you're a bit confused by it, just literally write divides, or you can skip the foreplay, I guess, because at this point you should be a bit proficient at it. Instead of dividing by 2k over 3, you're timesing by 3 over 2k. Okay. And you can probably do that in your head as well in one step. So that's 2/3 of learn. Okay, let's cancel some stuff out. So 3 will cancel here, and the k's will cancel. So you're left with 8 over 2, which should be learn 4. So you can see this again. So 8k times 3 would be 24k. This would be 6k. So that would go to 24 over 6, which is 4. Okay. And that's it. So that's the answer. I don't think we can simplify it anymore. Perhaps you can add the 2/3 into it, but that would make it complicated. Now look at the original question. We did all that. It says it's independent of k. So what does that mean? That means that no matter what value of k you pick, it will not change the answer. Now that is obvious because there's no k in the answer. So there is no k. Meaning the answer God's sake. I'm still getting used to this pen. First time doing this. Oh, get off, you bastard. What are you doing, man? God's sake. Meaning answer uh is, and you can be fancy, is invariant no matter what value of k you pick. So I'll just say in simple terms, answer is constant, right? Constant for any value of k. Which is just another way of saying Al is independent of k. Um, so I guess if you're a bit unsure, I guess think to like probability. So if we say two events are independent, that means one event does not affect the other event occurring or the probability of the other event. So they don't influence each other. So changing one thing doesn't change the other. They're independent. Okay. So they're like uh, kind of like they stay the same essentially. They're by themselves, so it doesn't, you know. So that's what that means. But yeah, even if you weren't sure of that, you might even get all 4 marks. I haven't checked the mark scheme. You might get all 4 marks just for working out the integral. But that line of that sentence justifying that is independent could is very beneficial. Okay, now we've got a slightly different integral. So this is inversely proportional. Now that you should probably recognise in GCSE. But again, if you're unsure, let's just work out the integral here. So 2k of k, let's just copy it. So again, it's the same process as before. 2k and k of, what was it? 2 over 2x minus k squared dx. Was that the right one? Just to check. So I do the wrong thing and then, yeah, it's the wrong one. 2x minus k. Oh, was it 2x minus? I swear I got brain. I got gold. Yeah, 2x minus k, not 2k minus x. Yeah, it's a good job we checked there. Obviously, I'm in reality, like you'd have the paper in front of you, so it should be easy to copy it. But for where I'm at, it's a bit difficult. Anyway, so that's the integral. Again, as always, one help to take any multiples out. So 2 of k, 2k of 1 over, sorry, 2x. That's k squared dx. Now, you should be thinking, what do I know? What integral techniques do I know? Substitution, probably a bit messy, no. By parts, no, not really. No product, really. Uh, Reverse chain rule, no, because this will definitely not differentiate to 1 or any multiple constant. Obviously, don't use the power rule. If you expand it, it's very, very messy. You'd get quadratic. Uh, and it's very, very, it's nothing really can do there. So don't expand it either, because you get 1 over a quadratic, and you really don't know how to integrate that most of the time. But there's one technique we do know. So if we have linear factors like this, or squared, so if we have a linear factor squared, that says I can use partial fractions, right? So let's just do it quickly. For 3 marks, it's a little bit awful. But let's do it anyway. So partial fraction should be the method that screams to you here. So before we integrate this, we need to express it in partial fractions. Minus k, and also it's a bit rough because there's a constant here as well. So it makes it a little bit more fiddly. So what does it say? So a over, and this should be the general form. You should recognise. Plus b over, I believe. If you're a bit unsure, try and add them together. So you'd get a of 2x minus k squared. Let's just check it works, first of all. It might not work. It might be a bx plus c. It might be a linear term. But if you're unsure, work it out. If you don't remember it, I mean, I'm a bit rusty as well. So let's add it first to see if it makes sense. So a of 2x minus k. Um, because obviously there's already an x minus k term here. So if we times top and bottom by 2x minus k, then you get this over that squared. So it matches the denominator here. Plus b, we don't need to add anything to that. So actually what happens here is we have a linear term. So we'd have 2ax minus ak plus b. You don't have to do all this. This is just to really reinforce it. You can skip right to the usual steps of like solving for a and b. Now, actually, that makes sense because there's two constants, uh, and there's two unknowns. So this is technically we can say this as 0x+1. So we actually have two equations and two unknowns. If we had like a polynomial, well, it is a polynomial, but if we had like a quadratic or something, if we added bx plus c, you would have three equations and two unknowns. It's not really how it works. So you should know if you get it right if you match the number of unknowns with how many equations you can make. So if it goes up to linear, so a constant plus an x term, and there's two letters, that's all you want. But yeah, so that should work fine. So now let's do it then. So we can compare directly the numerator, the one, with the numerator of this because the denominator is identical, and it is identical. So that means the numerator must also be identical. So one is 2ax minus ak plus b. Okay, so we can also say this is 0x, right, plus 1. So we want the x term is 0. So how are we going to do that? LHS is 1. So we know that the left-hand side, LHS, is 0, the coefficient. So then we need to make sure the coefficient of x is also 0. And the only x's here is a. So that would mean a would be 0, right? And we know the constant term, or the constant, is 1. So that means 1 has to equal minus ak plus b. But we know a 0, so b will just go to 1, right, to make that 1. And now it is. So I guess it's a pretty simple partial fraction then. So then the integral is what was it? 2k and k. Well, two lots of 2k and k. Of the fraction. So, of the partial fraction. So this fraction in here, the integrand, is identical to this, but we know a is 0 and b is 1. So this will go to 0 and it'd be 1 over that squared. Which is wrong, because that gets us nowhere. Okay, so because of that, hmm, okay, so what we've worked out there is, and this is how you know I'm rusty. We've worked out there. I think it has to be a bx plus c. I think. Yes, so that's how you know you're wrong as well, because if you get the original fraction, that does nothing. So we need to do. Yeah, that you should remember this. Oh yeah, I fucked up there. But you know, this is the reality of doing it live. Especially when I've done in eight. I've not done this touch math in absolutely ages. Uh, so what you need to say then is bx plus c. Okay. When you have a repeated factor, you need to split it like this always. Okay. There you go. I forgot about it at first. But there you go. See, I told you I'd mess up somewhere. But yeah, that's a good thing. Even if you mess up like this, obviously you are in the time limit. But you know, not the end of the world. But you know, if you clean mess up like this, trial and error a little bit. But I really, like I said, you really should know it. The partial fraction decomposition. I haven't touched it in a while, but now it will be in my memory, hopefully. Uh, so yeah, so let's equate them together, like I said. So a, so you want to times by 2x minus k plus bx plus c of 2x minus k squared. And that would mean if you compare the fraction, one is identical, the numerator, a of, I'm going to expand it actually as well. So 2ax, to expand this, 2ax minus ak plus bx plus c. And yeah, so now we can start comparing stuff. Let's get rid of this shit. Uh, there we go. Okay, so compare, so x squared coefficient is 0. So this is equivalent to saying as well 0x squared plus 0x plus 1. Okay. Is 0, which means 0 would have to equal. Well, there's no x squared here. Hang on, I think we messed up here. No, we won't be able to solve this. Oh shit, how do you do it? Because you would get 0 equals 0, but then you'd have two equations of three unknowns. Hmm. Tell you what you can do though. I'm dumb. See, we don't get it right. I got it. You don't even need partial fraction. I'll tell you because you can use reverse chain rule. Of course you can. Because we can just rewrite the power of the factor of -2. Minus, yeah. Oh man. See, I haven't done it in absolutely ages. Again, this is what the aim of all this is, not to get absolutely perfect. Although ideally in the end we get it right. But to show the thought process of how you should be approaching it. And yet, if you were to go down the partial fraction route, it'd be a bit messy. Uh, but yeah, what you can do then, you can say, well, this is 2 of the integral of 2k of k of 2x minus k to the minus 1. Uh, -2, sorry, bloody hell. God, I'm losing it, I am. -2. Now, actually, now you can use reverse chain rule. So, uh, okay, well, if but you need to think of something to differentiate, so probably let's try the bracket. 2x minus k. Um, Now, if we differentiate into this, it needs to be -1, doesn't it? Because uh, we're going to subtract -1 from the power. So -1 gets us -2. So then dy dx would be, use the chain rule here. The derivative inside the bracket, which should be 2 times by the power. And then what's in the bracket? -2. Okay. But obviously notice this is not the same as this. We have a factor of -2 instead of 1. So what you can do is you can just say -1/2. And then you'll just times this by -1/2 at the end to get -2 times -1/2, which should get you 1, right? So that's the integral here. This is the integral because if you then differentiate it, you get back to this. So the integral is going to be this function here. So that means that's going to be 2 lots of -1/2. And actually, you can bring the -1/2 out, can't we? 2 times -1/2 get you -1. Uh, of what? 2x minus k. Oh, -1 between the limits of 2k and k. Well, actually, -1. Hang on, let's just substitute it in first. 2x would be 2 times 2k, which would be 4k. 4k minus k gets you 3k. Minus, and then 2 times k, 2k minus k gets you k. So that's going to be minus. Now, actually, what does -1 mean? Well, it's reciprocal, so it's going to be 1 over 3k minus 1 over k. And then bring the fraction, the negative outside, inside. So to get 1 over k minus 1 over 3k. Now actually we can do some simplification even more because this is a 3 here. We can bring it as 1. And actually the only common factor, the only thing we need to scale it is 3. Because this is k and this is 3k. So this is 3 over 3k minus 1 over 3k. Happy? Because this go back to 1 over k. Just some GCC really there. And actually 3 minus 1 gets you 2 over 3k. Cool. So now that's the answer to the integral. Let's go back again. So it said, show that it's inversely proportional to k. So if something is inversely proportional to k, proportional, you should remember it's in the form. I'm not going to use k. Of another constant. Let's say alpha over k, right? So it's 1 over k with a constant, so a factor of alpha. So that's what it looks like here. K, well, it's over k, but scalar multiple. But if we see here, 2 over 3k is in the form with alpha, obviously 2 over 3. So it's inversely proportional to k. So integral is inversely proportional. And actually, this shows you we got it right because we get a sensible answer. And yeah, that's it. Oh God, oh man, yeah. I haven't done this at absolutely ages. Like, I haven't touched maths in years, seriously. So I'm getting used. It's coming back to me now a little bit, but yeah, I can still do it. Okay, now on question 8. God, what time is it? Bear in mind, 10:30. Okay. I've got about 20 more minutes. Probably end up towards we'll probably end up doing a half the paper today and half the paper tomorrow, maybe at another point. But yeah, let's go on to it. So now this is a trick one. So if you've seen this before, you should know this is going to talk about harmonic form, perhaps. Or it's going to look about what the minimum and maximum value of the function is using your knowledge of sine and cosine the graphs. Okay, so it's a modelling one. Hopefully, shouldn't be too bad. So the depth of water is given by this. So obviously, it looks like a sine wave. So you imagine as water it looks like a wave, if you will. So it goes up and down and up and down. So T is a number of hours after midnight. A boat enters the harbour 6:30 a.m. So with these modelling, really pay attention to the units here. T's number hours after midnight. So 6:30 is going to be 6.5 hours, right? So that's probably going to be 6.5 after midnight. So T is going to be 6.5 there, just to annotate. And it takes 2 hours to load its cargo, so it's going to be 8.5 after, right? The boat requires a depth of water to be at least 3.8 meters before it can leave the harbour. So it says find the depth of the water as it enters the harbour. So so we've just done it really. So enters the harbour at 6:30. So that's 6.5. Because at midnight it's 0, and then every hour, 6:30 a.m. is 6.5 hours after midnight, which is where this comes from. So all we have to do here is substitute t is 6.5 into the depth d. That's going to be 5. Oh, damn it. 5 plus 2 sine 30 times 6.5. degrees. And then we just shoot it into the calculator. Bearing in mind, this is in degrees and not radians. So make sure to bear that in mind. So 5 plus 2 sine. 30 times 6.5 gets you 4.48. I presume it's in meters. Cool. And that seems fairly sensible, right? 3.8 is there, so 4.48 is not really out of reach. It's not miles away. So yeah, that's probably the answer there. Make sure 2 key points. Make sure you know what the time converts to, and make sure you're working in degrees and not radians. That question I think is there to catch people out, but it's fairly simple. Now it says find to the nearest minute the earliest time the boat can leave the harbour. So it says here the boat requires the depth of water. I don't know what this is given. We'll see in a minute. The boat requires the depth of water to be at least 3.8 meters before it can leave the harbour. Okay. So, we know that's what we know at 4.48. I don't know what it's given now. But yeah, so let's convert this. So we do some modelling, convert it into maths, essentially, right? That's what modelling is. So I think it's a good idea. So it says the depth of water needs to be 3.8 meters. So I think we have to equate D to be 3.8, and then we solve it. So 5 plus 2 sine 30t. If I can write 30, that has to be 3.8. And naturally, now this is an equation to solve for t. So it's a trig equation. So that means 2 sine 30t has to be minus 1.2, right? 3.8 minus 5. 1.2. Yes, I did check that. Which means then sine of 30t has to be minus 0.6. Cool. So you solve this equation. Now we have the range 0t7 to 24, which means we can convert this to 30. So 0 is t, so just the range because t is not, it's 30t. 24, which means 0 has to be between 30t times it by 30. Now actually you get a massive number, so you get 720. So there's going to be many solutions to this, which is where you have to be a bit more careful. So, okay, but let's just solve it first. So, sine 0.6, so is this, it's really useful to sketch the graph. So let's consider sine of t is 0.6. So the sine graph will look like this. So that's 0, pi by 2, pi, or 100, not 90, 180 because it's in degrees, 180 to 70 for 60. So 0.6 is going to look there, roughly. Actually, let's make the sketch a bit clearer. So 0.6, so that's 1, so it's going to be like there. So there's going to be 2 intersections for every loop, right? So one where it's just across 180, one just below before 360. And a key point to note is the sine graph is symmetric, uh, like 90 here and 270 here on the left and the right of it. But also, if you yes, what I'm saying is essentially there. So if we were to break this up in two, um, this would be the same distance between here to 270 to this intersection here. So let's do the inverse. So what would you get? So we call this the principal solution, which is the solution when you arc sine this. That's whatever the calculator gives you is that. And actually, it tells us it's well, that's not right. Am I in radian? No, I'm in degrees. Oh yeah, no, that is in degrees. That's why it's so big. So minus 36.87 degrees. But that comes from extending the graph a bit more. So it'd be there. So if I just continue the graph forward, so so what the principal solution does, it gives you the closest to zero, which should be this. So this is far away from zero, but this is the closest solution here. If we were to continue this on the left. So actually, this mirrors this line here, this solution here, right? So if we add 180 degrees, no, 360, sorry, uh, add 360, you get 323. And that's one solution. And the other solution here, so I mentioned the distance is the same. So how to work out the distance? So do this answer here. Let's sort in the calculator. 323. This minus 270, which is 53. So 53. That's the distance here between this x point 270 and the intersection here. So because it mirrors the distance, we minus 53 from 270. So 270 minus 53.13. I should also, oh, I messed it up there. I should note this comes from 320. Hang on. I'm being really messy here. I really want more space here. Hang on. That gets you to 16, which is like 869 something. Store that in the calculator. So we've got ongoing decimal to store them in the calculator. Now these are the two solutions. These are the like two distinct ones I like to call them. Now the other property with sine is that they repeat every 360. So every other solution possible comes from adding 360 to each of these every single time. So we know that 30t then would have to be, let's do it in order, 216.869 or 323.13, dot, 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 dot. And we keep adding 360 until we reach this bound, right? 720. Oh, that's not too. I keep thinking. I thought 720 was a big number. I keep thinking it's in radians. I thought 720. If you do that in radians, you get so many. Oh, but that's not too bad. So I should probably specify it's in degrees. Uh, Actually, no, not necessarily. Actually, No, it is. Sorry, it is in rate degrees. Sorry, of course it is. Sorry, I'm having a dumb moment. uh, yeah. So then to get the other solution, you keep adding 360. So add 360 to this, gets you 576. And you add 360 to this, uh, gets you 683.13. Dot, 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 dot. Now, if we add 360 onto this, what happens then? Add another 360. You get 936. However, we adjusted that interval, so it has to be between 720. So actually, 936 goes above it. So that's all our solutions there. Okay. Which means t then divide by 30 each of them. Gets you t is 7.229 roughly. Then divide 323.13 divided by 30. You get 10.771. Then this by 30. You get 19.22. It says 89. I'd say 229. I'd say. Let's round it. And also this by 30. So that would be 22.771. Okay, cool. So they'll all do like 3 decimal points. So you have a good degree of accuracy there. Okay, so we've got 4 solutions, but which one do we accept? So also interpret it in context as well. So this is saying it's 7.2 hours after midnight, 10 hours after midnight, 19 hours after midnight, 22 hours after midnight. So what it's asking you here is the nearest minute, the earliest time the boat can leave the harbour. So we worked out part A. It enters the harbour at 6.5 hours. At 6:30 a.m. Sorry, it takes 2 hours to load the cargo. So that's 8:30 a.m. Now it requires the depth to be 3.8 before it leaves the harbour. Okay. Um. So when does it? When does it pass through 3.8? Well, we worked out. Yeah, that's what we worked out. So it reaches 3.8 at 7 hours, at 10 hours, 19 hours, and 22 hours. But we worked out in part A. Hang on. So it has to be at least 3.8 meters. But we worked out in part A. That's at 6.5 hours. It's 4.48 meters. So actually, when it reaches 7 hours, it's gone down from 4.2 meters to 3.6. So actually, it's going to keep going down. It's going to go down, then go up, back to 3.8 meters in 10 hours. So actually, the minimum time when it reaches 3.8 again, when it leaves the harbour, is 10 hours. So the solution is going to be 10.771. Okay. Um, so now what we need to do is convert that into minutes. Now this is where it gets really, really fiddly, and I'm not. Again, you have to take your time with this. So this is in hours, right? Hours after midnight. So that's 10 hours and another 7.771 of an hour. So we know it's 10 hours. plus 0.771. This is not rigorous, but of an hour. Okay. Now we can convert this into minutes. So we know that 1 hour is 60 minutes, right? That means 0.771 of an hour is going to be 60 divide. Well, what do you divide one by to get 0. Let's have a look. So 0. Uh, well, what do you multiply by even? So 1 times something gets you this. So it's going to be, well, simply, right? So it's going to be 0.771 because it's 1. So that means you times 60 by 0.771 as well, which gets you 46.26 mins, which means this part of an hour is actually 46.26 mins. So 10 hours and 46.26 minutes. To the nearest minute, it is, or so 10 and 46 minutes. If we round down, it'd be 46 a.m. Okay, that's your time there. And hopefully I got that right. But that's how I'd work it out. With these really fiddly ones, where it actually when it wants you to give it in minutes, when their numbers really fiddly, just go back to basics like this. I don't think it seems sensible to me. I don't know. I should check the mark scheme actually for that. See if I got it right. So I'm not spouting BS. Duh, 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 duh. Yes, 10:46 a.m. Lovely, lovely. Got that right. Just check that. What time are we on? 10:51. I'm gonna leave that there then. Actually, how many questions are there? Does it say? 14 questions. So yeah, so we're just over halfway. We're on question. We're about to do question 9. But yeah, obviously you shouldn't really spend this much time on the paper. I'm only doing this to explain everything terribly. Now, but I do hope it did help someone. But that's yeah. Um, yeah, but obviously I think this was the big problem, right? This integral here. I should probably go away, learn my partial fractions or whatnot. But yeah, that's the paper done. I'll have a look at it, but I think it should be okay. The answers. I mean, if it makes sense, which is a good thing to check your answers. Make sure it all makes sense like this. So this clearly is inverse proportion. So I probably got it right. Uh, yeah. This was a really fiddly question, but yeah, just take it easy, and you should get. I really recommend this strategy, by the way. Try and use ratios, simple ratios to work it out. There, break it down. Because they do, I think they do love asking questions like that where they want with modelling. They want you to convert something really fiddly into a unit, a different metric, a different unit, and you have to be really like fidgety, not fidgety, really delicate with how you convert it. But just go back to basics. Okay, so hours, but it splits it down to 10 hours, and then this part of an hour here. Okay. Yeah, so yeah, I'm going to leave that there then. Hopefully that did help. So again, it's very, 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 very different stream, very different. Uh, but yeah, like I said, this is part of what I like doing as well. And I do like helping people as well, especially with stuff I can do like maths or whatever. If anyone does see it, will help someone. But yeah, like I said, this wasn't perfect for two reasons. First of all, I'm really new to like this sort of writing. Like I do apologize, my handwriting's a bit messy. I don't know. Part of it just have shit handwriting. Some of it's because I'm getting used to writing on like a digital pen. And yeah, get used to the software and everything. But also I haven't done maths like this in years. I'm surprised I've got it still, pretty much. But yeah, but I think that's good as well, because it shows, oh, where do people like where the slip ups, where do people take more time, what takes more thinking, where are the flaws are, so then I can explain it. Because I'll go through the step obstacles myself and then obviously explain that, get out of it, help solve it, and then obviously help others think about how they approach a paper. That's the idea with this anyway. Like I said, it's not just a fucking be a mark scheme. That's not the point of what I'm doing here. Like I said, you want the mark scheme, it's available on the website. But yeah, that's the aim of that. So yeah, thanks for watching. I hope this helps someone. Like I said, I do gaming and this now as well. But yeah, I don't know what I'll do next, but I will finish off this paper. Absolutely, I'm not going to leave you hanging. But yeah, this will definitely be on my YouTube. It'll be on a different playlist if I can work out how to do that. And yeah, that'll be part of the series I'm going to do now up until when the exams are. Um, to help. And I really do want to focus on this educational bit of it. Potentially, I might start doing like topics and stuff like that once things die down with exams or whatnot. So yeah, hopefully I'll be like, I don't know, have my own maths information, maths videos or streams or whatever, uh, ready to go. But yeah, that's all for today. Try and work out how to end it on here. Yeah, because I'm usually I stream on PlayStation, but for the first time I'm on the PC now. But yeah, I'm gonna leave that there then. And yeah, uh, hopefully it all went well. Hopefully it's on Twitch all right. I'll upload it to YouTube and whatnot. Any questions, obviously ask, please. I'll try the best I can to answer it. And I'm gonna leave it there then.